Hello. Hi, everybody. I just want to jump in right away and say Interchain Security is almost here, and it's going to be awesome. Okay. So, my name is Daniel Tisdall. I'm here today, very happy to be in Seoul. And today I'm going to be presenting Interchain Security, a new upcoming feature for the Cosmos Hub. Interchain Security is going to let you launch new blockchains into the Cosmos. It's going to let you scale horizontally while sharing security from the Cosmos Hub, which is a multi-billion-dollar market capitalization chain with a global community. In short, Interchain Security lets you launch arbitrary high-performance app logic safely, securely, and easily. So first of all, before I jump into the presentation proper, a little bit about myself. So I'm here today with my colleague Jelena from Informal Systems. We're a globally distributed organization, and we're core developers of Cosmos. What does that mean? We develop applications, tools, and services for improving dev velocity, testing, and confidence of applications for blockchains in general and for Cosmos blockchains especially. We contribute to infrastructure, so we're running validators, relayers, and we're also contributing to Rust implementations of Tendermint and the Hermes relayer. Finally, we're also core contributors now to the Cosmos Hub too, and that's the team that I'm a part of. Okay, so today's talk format. My session is going to consist of two parts, a talk part and more of like a hands-on demo workshop part. So part one, I'm going to be starting fairly basic with Cosmos, blockchains, how everything works, how the stack works. So proof-of-stake blockchains, Cosmos, the Cosmos ecosystem, going through the stack, Tendermint, the SDK, and the relayer, relaying packets with Hermes, our Rust relayer, and then Interchain Security, of course. For part two, I'll be getting more into the why of Interchain Security, why it's necessary, and why it's such an important feature. I'm going to be showing you how to launch custom app chains which can benefit from the multi-billion-dollar market capitalization, and how you can leverage Interchain Security to launch completely custom app logic with your own governance, your own tokenomics, and your own gas economics. I'm also going to be showing you a bit about how it works, so going into some details of the protocol. For the workshop part, I'll be showing a live demo of two participating chains. I'm going to be showing you how to debug and observe the system. I'll show you how to develop your own consumer chain. I'll be doing a code dive and then answering some questions. So let's get into it. Okay, so many of you are very highly technical. You've been in blockchain for a while, but others have not. So what is a blockchain? It's a series of blocks which contain state about the application. Okay? So over time, new blocks are published into the network, and each block contains some data about the state of the application. And it also contains a link to the previous block, a cryptographic hash. So in this case, in this example that you see now, we have the first block, Alice, has $5. The second block, Alice has $9, and we can see in the second block there is a link with an arrow to the previous block. So this is as simple as a blockchain gets, and what does it mean? It means you cannot go back in time and rewrite history once the blockchain has progressed sufficiently far. So what is proof of stake? Proof of stake is a mechanism for showing that you have some skin in the game that is going to allow you to participate in telling the blockchain what happens next. So there's two ways currently in the blockchain world, two popular ways to actually write new state into the system. Proof of work and proof of stake. And both of them require you to prove that you have something that others don't, which means you have skin in the game, and you're allowed to decide the next transition. So proof of stake is the mechanism that Cosmos uses. And what does it mean? So proof of stake uses the actual cryptocurrency itself as the voting mechanism. So the more stake you have, the more likely you are to be able to vote on the next transition of the system. What we see here in this image is a list of what's called validators, and this is the top 11 validators as of yesterday who were validating the Cosmos Hub chain. So we can see the list here, and the cumulative share of voting power. So voting power is derived from the number of tokens which are staked to that validator. So each of these is an organization, a company, or an individual, who can be anonymous or not, who has been delegated to by the community, by you, by individuals, by institutions, to have skin in the game and to decide what happens next in the blockchain. We can see that the cumulative share increases as we descend down the list. So for example, stake.fish has roughly 6% of the tokens delegated in the system. And one crucial thing about proof-of-stake chains is that you need a cohort of agreeing validators with a certain percentage of voting share to decide what happens next. So due to the way the Tendermint consensus protocol, which is the part of the system that decides, which coordinates these validators and decides what happens next, it's required to have 2/3 of the voting power, or 2/3 cumulative share, so 67%, to decide what happens next. So we see that that takes, in this case, significantly more than 11 validators, because here we have 48%. So we've talked about proof of stake, but what does it actually mean if you're developing? How can it help you think about blockchains in maybe like a higher level way and not worry about the details? So it really means it's a computer that you vote on. And because the state machines are completely arbitrary, albeit deterministic, you can think of a blockchain as really a global computer or a collection of global computers that are voted on. So it's just like voting in an election. You vote for what happens on the computer. So the computer can be anything. It can be, maybe we'll see they're as powerful as, you can have as much computation on chain as you can on a MacBook nowadays. And in this slide, I show you the reality. So this is obviously simplified, this Alice dollars example, but here we're seeing the reality of the state on the chain when using a Tendermint system. So we can see we have the same thing here. This app state is like the application state, so Alice has $7. And here we have some changes in the validator set. So this is really, it's these changes in the validator set that happen block by block as different validators lose and gain tokens that decide who votes next on who votes on the next block. So over time, the voting set changes. And this is quite crucial for Interchain Security because it's exactly these changes which are transmitted cross-chain and allows the crucial features of Interchain Security, which are shared security and scalability, horizontal scalability. Okay, so we've talked about proof of stake, we've talked about blockchains. Now, Cosmos. So you're at a Cosmos hackathon. I'm guessing you know a lot, but maybe not everyone does. So Cosmos refers to a few things, but it's mainly talking about an ecosystem. So it's an ecosystem which is using Tendermint consensus. It's an ecosystem, by and large, that's using the Cosmos SDK, so the source development kit. And it's an ecosystem of many chains communicating through IBC, which is, your inter-blockchain communication. So we can see here from this website Map of Zones, Cosmos, the many popular chains in the Cosmos network, by no means all of them, and each of these links is an IBC connection. So the brighter the link, the more application packets are being sent. So in this one, Cosmos Hub is the selected network, so we can see who is communicating with the Cosmos Hub. Okay, so now I'm going to go a bit into the stack. So we can see a layer of validators at the bottom, which are, as I said before, individuals, institutions, DAOs, and they are deciding what happens by running hardware, of course. So they can be doing this on their Raspberry Pi, although unlikely, or they could be doing it in cloud or in, I don't know, a back room somewhere. Above that, we have Tendermint, which is the layer, the consensus layer that organizes the validators. So it decides, it allows the validators to communicate in an ordered way to eventually come to an agreement, to come to a consensus. And the crucial thing about Tendermint is it's communicating with the SDK to learn the voting power of the validators to get this Byzantine fault tolerance that you probably heard about. Above Tendermint, we have the SDK. So this is your application layer. So this can be coded in Golang using the source development kit. You know, we can see even on top of this, although not pictured here, you have things like CosmWasm. There's many ways to kind of have this interaction between your application and Tendermint. And then finally on top, we have the IBC layer, inter-blockchain communication, which is what's giving you all the power to do the cross-chain applications that Cosmos is becoming so well known for and is doing so well in. So IBC lets you establish connections and channels with other chains, and it lets you do arbitrary communication between those chains, just like how you make a TCP connection when you connect to a website. So now I'm going to dive like a little bit into each layer of this stack to tell you like how each part works in more detail. So we have the Tendermint stack. We can see here each of these black disks, you know, roughly corresponds to one of these black validator disks. And what we have here is 4 nodes, which are communicating via this represented with a hexagon P2P layer. So this is kind of the agreement layer. We can zoom in on this a little bit and see what's taking place in a full node. So a full node is the name of a group of processes which can be run on one machine or multiple. In theory, I think mostly they're run on a single machine, off in the cloud somewhere. And you have 3 components. So you have the actual application that written with the SDK. This is doing your app logic. This is, you know, transferring money between accounts, etc. You have Tendermint core, which is the extremely high performance layer which is doing the consensus and answering queries. Tendermint core consists of, you know, an RPC receptor to take messages and add them to the mempool or answer queries. A P2P endpoint, which is going to allow the gossip protocols, which are needed for consensus, and then a signing part, which allows you to use, you know, cryptographic signatures to sign messages so that nobody else can act on your behalf without your permission. Okay, so that was Tendermint and the validators. Now we can go up slightly to Tendermint and the SDK. So you may have seen this diagram before or a similar one. And what this is showing is the connection between your state machine or application built with the SDK and your consensus layer, which is part of Tendermint core, which was that green rectangle we saw before. And the crucial part here is this ABCI, so Application Blockchain Interface. It's the name of a pattern of message passing between Tendermint and the SDK, which is going to bundle transactions. So it's going to bundle messages sent from members of the public into mempool. It's going to order them, and it's going to send them, once agreed on, into the state machine to execute the next transition and make something happen on chain, right? So this is now a picture of ABCI. So what happens in a block? You receive, this is now, you can imagine this happening on one node, so this may be happening on a single piece of hardware. And this is done by each validator. So when a block is received by this validator, so a new block in the chain, the block's received, there's a call to begin block in the SDK, which is going to give your application a chance to do anything it might want to do on a regular basis, right? So not based on a particular transaction, but something based on, for example, time, timeouts, just general cleanup, that kind of thing. And then you have a series of deliver TX calls, which are going to take the transactions which are bundled into a block and submit them one by one in sequential synchronous order to the application to make changes on the state machine. Following this, you have an end block, which is similar to begin block. The difference is mblock needs to also send the new voting powers as decided by application logic to Tendermint to allow Tendermint to decide which validators are going to vote for the next block. Commit is basically the code that signals everything is finished. It's going to write things to disk. At that point, the block is concretely stuck forever, essentially. So what's so special about the Cosmos SDK, and why are people writing so many applications using it? Well, you may notice already if you've been doing it yourself for a while, but it's simple. It's not written in Haskell, it's written in Go. It's easy for people to understand. The code is straightforward. There's no reinventing the wheel. You don't necessarily even need to know about blockchains to use it because of this ABCI. You just handle transactions. And there's a lot of documentation. There's a massive community around it. It's modular, so it consists of a series of modules which you can include or not include as you wish. In practice, we see that many of these are included in most projects, staking module, for example, slashing. But in principle, you're free to do as you want with these, and we're seeing cool modules come out all the time, right? So Interchain accounts was already talked about. There's things like this. And of course, Interchain Security. So it's customizable due to this modularity and simplicity. It's easy to get in there to hack things, change things, swap things in and out. So that's why Cosmos is so great, I guess. So just to give you an idea, to make that a bit more concrete, what are these modules that you may include? Here's a small list. This is by no means all of them, not even the default set. So you have auth-z, which is a module which lets you delegate specific actions to accounts so that other accounts can do actions on your behalf. Okay, so this is kind of like an equivalent example on Ethereum would be like you submit to a smart contract, and then after that, the smart contract has the ability to send money on your behalf. You have bank, which is the module that actually stores account balances. Distribution, which is the module which takes rewards from validators and from validation and sends them to validators. You have evidence. So evidence is a very important one, although hopefully you won't see it being used too much because it's dealing with bad behavior. So when a validator is included in the active set, but they're not actually doing work, so for example, it would be great for a validator if they could be included in the set and not actually pay any compute on AWS to do any work, right? But evidence prevents them from doing that because if they do that, they will be penalized for downtime. So that's the evidence module. We have governance. So governance is what's allowing all these DAOs. It's what's allowing proposals. It's what's allowing the chain to migrate in ways beyond the normal transactions programmed on chain. So governance is mostly using voting power to decide on major things like upgrades, like reverting transactions, this kind of thing. And crucially for Interchain Security, it's through governance that you allow what we call a provider chain, so the Cosmos Hub, to take on a new chain and give that chain security and scalability. We have the Mint module, which is the module that creates new tokens from nothing and burns them. We have slashing, which interacts closely with staking and evidence, and is the module that's responsible for burning validator tokens when they do one of the misbehaviors described earlier. The staking module is what you will know if you've ever delegated. So when you do an action like delegate, redelegate, or undelegate to a validator, it's the staking module that handles that logic. It's the staking module that gives you your refund after the unbundling period has completed. And it's the staking module that changes the balances of the validators based on the number of delegations they have. Upgrade, I'm not personally actually too familiar with it. I'm guessing it's the one that does the chain version upgrades. Okay, so we've talked about the SDK and some of its modularity. Now let's get to IBC. So as I said before, IBC is very generic transportation protocol. And it lets you send packets one by one in sequential, so ordered or unordered order as you wish. And it requires what's known as a relayer. So chains do not actually open a network connection to each other. What they do is when a packet is sent, that packet is written to the block state, and then it's an external service called a relayer that observes this commitment of the packet and forwards it to the chain that the packet is addressed to. So the relayer is depicted with this red diamond. We can see the packet is not really sent, but is more committed to chain A. The relayer sees it and forwards it. So the relayer is just like Tendermint, just like to some extent the application layer, a piece that is really computationally expensive because you can quickly, the words on the tip of my tongue, you can quickly absorb all available bandwidth, like on CPU, also like I/O, network I/O on a relayer. So this is something that's really important to get good performance on. At Informal Systems, we have a team developing the Hermes relayer, which is a high-performance Rust implementation, which I hear is also becoming kind of the most popular in the ecosystem these days. So please check that out if you ever want to be doing some relaying. And don't forget, you can reap rewards and fees for relaying too. This is a small code snippet that shows you how you might set up Hermes. So you need to specify some keys to pay fees. No one works for free, right? Once you've done that, you can create a connection between two chains. So in this case, we're creating a connection from chain A to chain B. And we have this client field is the name of the type of light client used. So a light client is a piece of logic that runs on the relay node itself and also on chain that allows you to trust blocks when they come in. So you cannot, if you ask the network for a blockchain block, you need some way of knowing that it's one that's actually on the blockchain, right? But you don't want to do that by downloading the entire blockchain from the first block, because there's a block every 5 seconds, so this will take a while. So what a light client does is it can use like a binary search to bisect the list of blocks, starting from a trusted header, and this allows you to accept new headers, new packets, without downloading the whole chain. Once you've created a connection, which you can imagine is kind of, this is kind of like, on the internet it would be like someone has found a route for your packet. So this is like kind of like knowing the route for your packet and saying that route's okay. So both sides agree this is an okay route to use. And the channel is now the component that lets you communicate between different modules, different SDK modules, right? So you create a channel and you specify ports, and then in your application you can route ports to different modules, different message handlers. So you can have many channels between even two chains. In this way you can have different channels for different purposes and different types of channels, so ordered and unordered channels too. And then we have Hermes start, which is going to actually start the relaying process and quickly absorb all your CPU, I imagine. Okay, so why was that interesting? Mostly to give anyone who's newer a kind of overview and an insight into why it matters that we're doing Interchain Security. So I said it once. Interchain Security is going to give you a way to launch completely arbitrary, custom, and creative high-performance app chains safely, securely, and easily. So it addresses two goals, two problems which are kind of not addressed sufficiently by any existing solution in the ecosystem. So we have, let's say, two major problems we're solving. Sharding, which is this scalability concern. So sharding is a kind of term for breaking your application into multiple pieces so that concerns are separated and the actual computation can have more scalability. So if you shard your your application or your applications or your system of applications, this allows developers to develop on each piece by piece, and it allows you to utilize different hardware, even more importantly, to get more scalability. So why is this a problem? So we're seeing that on chains like the Cosmos Hub, we have a lot of people trying to make proposals, trying to get things running on the hub. But don't forget, every piece of code that's running on the hub is actually taking up some kind of CPU cost, right? So if there was a way to kind of share this computation among different hardware, among different data centers, that's a net win. And in this manner, if you do this successfully, you can scale and it's horizontal scaling, so it's nearly unlimited. You may just need some coordination. Security, what else? We're seeing a big problem with security. As I said before, you need this validator set with some skin in the game to prevent an attack. So due to the way the voting, so Tendermint consensus works, it's possible to dictate what happens on the chain if you have 67% or more of the tokens or the cryptocurrency on chain. So this clearly is not, it doesn't matter if your chain market cap is billions of dollars, but if you're a new developer and you're trying to make a fun app or even a very serious, important economic application, it can be very hard to bootstrap this network in a fair way so that you don't have already this problem of the rich getting richer, and especially the problem of the low market cap, which might make you susceptible to institutional attackers with a few $100 million to spare to attack your chain. So Interchain Security is really tackling these two problems. So what are we getting? We're getting sharding with shared security. So we have one solution to solve two problems. I'm going to go more into why this is so important and some downsides and problems with the current approaches to solving this. So let's talk about sharding. So what is happening for, security actually. So what is happening right now is we have chains being created, and they're having a really hard time to fairly allocate these tokens, right? So a common way to do this is a stake drop or an airdrop, where they're taking a snapshot of another chain, and they're essentially they're dropping tokens in the genesis to people who already have a lot of tokens on other chains. So this is a rich get richer problem, and it's also a low security problem, right? We're also seeing, this is very difficult for people new to the space to get in on the action, let's say. We have these established ecosystems, these established communities and networks, these established connections between people who know each other, and they're mostly all interacting with the dominant established chains, right? So for example, the Cosmos Hub, Osmosis, Juno. This makes it very hard for people to get on board, and especially to get validators who are professional companies, professional DAOs, to actually take on their chain and do the work of validating their chain to run the chain. So what we're having here is an incentive alignment problem. There's no incentive necessarily for a validator to take on work on your chain. They're betting on your project, essentially. So shared security, interchain security is removing the need for validators to bet, because the design of the system means they will be validating on your chain, but you will be getting the security of the Cosmos Hub, and of course there's a cost for that security. You'll be giving some rewards or fees to the validators, so it's a win-win. You get security, the validators are getting rewards in the form of tokens. So let's see an example where this has gone wrong in the past. So the infamous Proposal 16 from Juno, there was a stake drop within the last couple of months, and if you've heard the story, it was gamed. There was a individual account who received an outsized number of tokens, which really was damaging for the economy. And there was a very contentious vote to decide how to deal with this situation, which resulted in, so this vote you see here is a vote to to basically undo that allocation of tokens to that individual. So you can see just by the number of no votes, this is a contentious issue which just completely disappears with Interchain Security. Okay, now, scaling. So, I'm just going to take a break for a sec. Okay, so I've talked about security, now about scaling. Why does Interchain Security let you scale, and why is no existing solution sufficient? So as I said before, we have a lot of people trying to get computation on chain, and all of that computation is utilizing CPU, right? This cannot scale forever, clearly, and it's the reason for why, for example, Ethereum gas fees are so high. Ethereum's running thousands of smart contracts, and the reason gas fees are so high is because you're bidding up the price of computation. You need to bid for computation. So if we can horizontally scale to multiple machines, aside from coordination, you have unlimited scalability in this way. So yeah, we can see an example of why this is needed. There was a proposal to get smart contracts from Cosmos onto the Cosmos Hub, and this, of course, was predicted to lead to the same situation as Ethereum, so it's going to bid up fees massively and just increase the workload for validators. And the proposal didn't go through, as you can see. So it's clear from both of these examples that the existing solutions are not sufficient. So we think we can do better. With Interchain Security, you get both of these. You get scalability and security. And so I have some examples. So the feature is about to release. We have a lot of people about to join. Just two of many examples. We have Quicksilver, which is a new liquid staking token, new liquid staking project. And they have said they are going to be using Interchain Security. In this way, they avoid the problem I mentioned earlier about bootstrapping a fresh validator set. And we have plans for a consumer chain. So a consumer chain for Cosmos. So instead of having to take smart contracts onto the Cosmos Hub itself and utilize even more CPU, we can create an entirely new chain or chains running Cosmos contracts, which can have their own economic models for how they take bids for gas and how they run smart contracts. So why are these guys signing up? Well, it's clear they get the security, they get the scalability, and they get the community of the Cosmos Hub. So I want to make very clear that Interchain Security is very much an infrastructure layer. It should be invisible for you, for users who are creating new apps, new blockchains. It doesn't restrict you. In fact, it frees you up. You can design whatever kind of tokenomics you like. You can design whatever kind of gas economics you like, whatever kind of auctioning you like, whatever kind of staking rewards you like, whatever kind of governance you like. So it should be a completely invisible layer. Okay, so let's see an example. We have our example with, this is a custom consumer chain. So this is imagining the scenario of someone coming, and they're not going to be using the defaults. They want to do everything themselves, right? We can see that this user, this developer, this organization has elected to have their own native token. Of course, you can do that. You don't need to use Atom. You can create your own token or tokens. Okay, so they've decided their gas model is going to be paying gas fees in their native token. They're going to have inflation, which is what we see already in practice in many chains. And how it works is, of course, as I said before, it doesn't come for free. They will do an airdrop to validators and delegators. So in this way, the validators are rewarded, and every individual who delegates to those validators are rewarded. They're going to have in-protocol actions such as voting, liquidity pooling, etc. So completely custom chain without this bootstrapping problem and with high scalability. There's also plans in the works with smart contracts. So we're going to be launching right after V1, so immediately, with a contract chains, so CosmWasm chains. The default here might be for users to pay gas fees in atoms. Okay, that makes things predictable. It gives a common market. It's connecting to the existing community. As before, hub delegators and validators are getting rewards for their work. And we're seeing that the fees can be sent directly to the community pool to help with governance, to decide the kind of progression of the distributed organization. So it's really a layer, Interchain Security is really a layer that lets you be creative. It doesn't put restrictions on you. And we have many projects shipping soon, which are going to come with some custom defaults or allow you to, example, put smart contracts straight on there. Okay, so now I'm going to go a bit into the protocol and how it works. Just you guys are technical guys. I think you might find this interesting, and it might help you develop your own consumer chain. Okay, so I've said before that what this is allowing validators from the hub to validate on other chains and get rewards for that. So the way the protocol works is you have two chains running completely separately, or it's more like a spoke model. It happens that two chains are drawn here. So you have a provider chain, the Cosmos Hub, and you have one or more consumer chains, which are sharing security from the hub via this way of sharing validator voting power between the chains via IBC. So in this way, we can see the two stacks here, and notice the validators are shared here. So I'd like to emphasize, this does not mean the validators must be running the two chains in the same place. They can be in data centers across the world. The only thing that's needed here is some cryptographic relation, right, to prove that the validators are the same, so some private key, ultimately. And how the protocol works is when validator voting power changes on the Cosmos Hub due to delegations, undelegations, slashing, the updates are shipped to the consumer chains, so broadcast to the consumer chains. And it's these updates which are received and stored on the consumer chain and transmitted to the own tendermint, the own instance of tendermint of the consumer chain. So what's here is kind of an implementation detail, let's say. So this is the unbonding completions. This is important because you may have noticed if you've ever tried to undelegate, you have to wait a while. So you have to wait 3 weeks to get your tokens back once you undelegate. So this is intentional because it means you have skin in the game for a while, and it means you can be punished. It stops the situation of misbehavior and then undelegating and then not being punished for that misbehavior once it's detected, right? So that's what this unbonding period is for. And this is very important because it's the skin in the game on the provider chain, so on the Cosmos Hub, that's really powering the security of the consumer chains. So what this unbonding completion is about making sure you cannot completely unbond everything on the Cosmos Hub before you've also unbonded your voting power from the consumer chains. So in practice, this is an implementation detail. You won't see it because this unbonding time is going to be set, a day less than the unbonding time for the provider chain. So this is kind of implementation. Yeah, let's dive into this a little bit more. So when you bond tokens, you receive voting power, and it's consumer validators, so the same validator set, although different hardware, that's doing the voting and collecting rewards. So the rewards can be in the form of native tokens on the consumer chains, or atoms, or any combination you can think of. So the only thing that's important here is the incentive alignment. So how are you going to convince validators to validate on your chain? Presumably, they will be interested in some kind of reward. But this is really up to you to decide economically, and it's up to the community and the validators to accept your proposal and to accept it. So this leaves a lot of room for customization. And bad behavior on the consumer chains. So the way the security works is the validators are going to be punished for, not only as it is now, for misbehaving on the provider chain, but they're also going to be prevented from misbehaving, so trying to confuse consensus or just having downtime and not validating on the consumer chain, because any kind of infraction or any kind of evidence from this evidence module that appears on the consumer chain or is submitted to consumer chain is transmitted via IBC to the provider chain, to the Cosmos Hub. And it's there that the provider validators will lose their tokens if they misbehave. And yeah, so we have also, as I mentioned before, this unbonding to prevent this problem of unbonding after misbehaving but before being detected. So these three pieces are leveraging IBC. Okay, so this is another diagram showing more or less the same thing, but maybe with a bit more graphical detail. And you can see what's going on here with the unbonding. So when somebody unbonds on the hub, there is a packet sent to the consumer, and then the unbonding period must elapse on the consumer before it is then acknowledged back to the provider, and the provider can finish unbonding. So invisible in practice, but interesting if you're developing. Okay, so how do you deploy? How do you take this custom consumer chain and get it running? How do you bootstrap it? So as I mentioned, the only thing you need is this incentive alignment, so some sufficient rewards to get people interested in your product, in your chain. So the steps are really this simple. You design your chain, you write your chain, you test your chain, you submit a governance proposal to the Cosmos Hub, and if the validators are interested, if they like your project, if they're happy with your reward scheme, they're going to accept it. And then it's up to the validator set to literally just start the binaries and start validating a new chain on completely separate hardware. All communication is through IBC. This is, I would imagine, quite beneficial in many ways. You know, validators can be sizable organizations. They can have separate teams for separate chains. And so this gives you both organizational scalability and this hardware computational scalability. We have, as I mentioned, a few projects kind of bursting who can't wait to use this, and I can't wait to see them use it. For example, probably one of the most impactful ones that we're going to start with is this CosmWasm chain, or chains, which are going to be consumer chains who are kind of sharing security and getting scalability through Interchain Security, and sharing security from the hub, where you can run arbitrary smart contracts. And because this chain is freed up from dealing with anything it doesn't want to deal with, right? So this can be a completely specialized consumer chain for a single smart contract, a bunch of smart contracts, a smart contract market. This is really giving you a lot of freedom. So this integration with CosmWasm, I think, is going to be very interesting. So just to go into the diagram a bit, you may have a custom consumer chain. You have convinced the hub, either through some social networking, a good reward scheme, a sensible proposal, and a well-tested binary, to accept your proposal on chain. So vote, yeah, can maybe zoom in here a bit. So we have this CW20 consumer chain contract, consumer chain, and we can vote yes, and we can see the vote end time, and I'll show you later, but this proposal will come included with a start time for the consumer, meaning the consumer on command is going to start running. Okay. Yeah, I would like to mention we have a team working on a tool for this. So we have a CLI tool in the works, which is going to make this whole process of starting smart contract chains much easier, because it will do everything for you. For example, validators who accept the proposal would like to know that the hash included in the proposal actually relates to a particular binary version, and that binary is compiled from a particular piece of source code, so they know what's going on, right? So we have tools that take care of all these steps, all this validation and checks, and make things very seamless. Okay, so that ends the talk portion of the session. Soon I'll be giving a workshop. I'm just going to take a few minutes break to catch my breath. The workshop's going to include a live demo. I'm going to show you how to observe and debug the system. Talk a bit more about developing your own consumer chain, so how to write the logic for that. I'll show you some snippets, some interesting parts of the code, which are going to be interesting if you're developing using this, and have some time for some questions. So to reiterate, Interchain Security lets you launch high-performance app logic safely, securely, and easily. It's here and it's going to be awesome. Thank you. Clone this and have a look. Hello. I'm ready to start now with the more hands-on part of the session. So I'm just going to launch right into it. Hopefully some of you had a chance to clone the repo and have a look at the instructions and play with it yourself. Right now I'm going to get straight into that. So bear with me because now it's the live part. Yeah. Sorry, can you repeat?
Yeah, I have a question of governance. You mentioned that like process clean in the case of bad governance or trouble governance going crazy. My question is, I understand how Interchain Security uses secure.hub by a very secure environment. But my question is, it doesn't seem to get rid of the issue that this is happening made. So if that issue came up, someone would try to do something on how to avoid it on the governance. Someone has to vote somewhere, right? Like, vote can happen.
Yeah, so the question was, Interchain Security doesn't necessarily solve the problem of decisions still having to be made ultimately, right? So yeah, you're right. I mean, the point of it is it's an invisible layer. You can design your consumer governance however you want. It's complete freedom. You can write arbitrary logic to govern your consumer chain. So the question was, does the hub decide when to upgrade? I'm not sure if like any concrete decision has been made. I don't know, basically. I think you can just have either. I don't see why I think you can just have either. Like you could submit a proposal which would make a commitment in the proposal, the initial chain proposal, that all upgrades are going to be made by the provider. Or you could, just have this a Boolean to say, oh, okay, if this Boolean is false, actually they'll be made on the consumer. Okay, so I like this question. So yeah, so it's very difficult to hear you, but I think I get the idea. So it's really, the question is like really about how it works when you have, conflicting or proposals happening both on consumer and provider. So this is something I suggest that people think about in creative ways. I know there's a team already who's working on this. So exciting to see what comes out of that. I don't have the answers. Like I said, Interchain Security is an open layer for you to do whatever you want. So it's okay? It's really hard to hear you with your mask. Yes. I think for V1, so we're doing a very short release cycle, so we're aiming for V1 like in the next couple of days. I think it's probably just on the provider, but there's no reason this can't be changed for V2, which is going to come out like probably in a couple of weeks. Provider. Yeah. Yes. Okay, thank you. So yeah, just to recap, the question was, in V1 of the project, who will be upgrading the chain? I think it's the provider. Yeah. Okay. So I'm going to now continue with the with the hands-on part of the session. Yeah, so hopefully you've had a chance to take a look at this link. I can show you roughly what that's all about. Yeah, so we have this README with some instructions how to get started in a hands-on way, how to see your own demo, how to install some binaries to get started with your development. This repo includes 4 instructions, so it also includes a script to check you have all the prerequisites. There aren't many, it's just to download and install the binaries, check out the repo, need some utilities, Node if you want to start the Explorer. Okay, so I'll just get right into this. What I'm going to show you is an instance of a provider chain and a consumer chain. And we'll see how the voting power changes are relayed and reflected on the consumer. So a simple demo. Okay, so we'll start the Explorer. Oh. Strange things are happening to my resolution. Okay. Okay, so we've hacked together this fixed chain explorer just give a nice interface to see a bit what's going on. And yeah, so we're going to have much similar to that diagram I showed earlier on. Let's see. Yeah, similar to, okay, we have Flickr. Okay, I don't know what's going on. Yeah, so very simple setup, 1 provider, 1 consumer, and we're going to see some changes reflected. You can follow along. Hopefully, maybe you already tried, so let's just see. We have some scripts. Let's launch the chains so I can show you a bit what's going on here. Okay, so this script is going to set up 2 nodes locally in these C and P, so consumer and provider directories. It creates key pairs and the proposal for the consumer binary. So this consumer has barely any logic. It's a blog post application. So if you've ever used Ignite CLI, it's going to mimic that very closely. So we have some simple steps. So some configuration. We're going to start with just some delegation to play with and the single validator. We init the provider. We add some keys. You can see that, okay. We generate the initial Genesis transactions to get a single validator going. Enable the endpoints. Start the provider. We create the consumer chain proposal. So you can see here like the binary hash, the spawn time. And we submit this proposal. We're just going to immediately vote yes to get this proposal to go through. So this is a chain, with tweaked parameters, so it's not like a 2-week voting process. We are going to init, once this vote has passed, we're going to init the consumer chain. We're going to add keys for it, add the Genesis account, copy in some Genesis state. So this part is a bit tricky, I would say. But for example, we have tools coming out to make this easier, including this tool that particularly handles the COSM-WASM chain, consumer chain use case. So yeah, we're going to just make some tweaks here, and the final instruction is to start the consumer. So I'm sorry about the pixelation, it's a bit pixelated. But we can see here we have an Explorer, so we can see the consumer now at height 20 and the provider at height 39. If we see what's going on in staking, we have the validator just with the name Fizz, 1,000 voting power. We can see this reflected also in the consumer. So the consumer, it kind of takes like very small, it just takes voting power, like voting power public key relations, right? So like you don't have the full staking module here. Okay, so that's all good, but can we actually see this change? Okay, so I forgot, we better relay. So that was just showing the initialization. So this voting power was exported in the init genesis for the consumer. That's why it's showing on the consumer. But we should now start Hermes relayer, so this high-performance Rust relayer, which is going to start transmitting packets between the two chains to carry out things like the validator power changes, carrying out. It's going to send any slashing requests, so for downtime or double signing. So wait a little bit here. Yeah, so we have a block time of a few seconds, right? So the handshake has a few steps. Each step requires at least a block, so we have just to wait a few blocks here. Yeah, so as I said, this is the consumer application here is a blog post application, so it's the simplest one you can get. I'll show you guys just after this part, like how you can just get in there and change the code straight away. Okay. Okay, so that's Hermes is now started. Let's see what we can, if we can see a change happen live in the voting power. So I've got this like delegate script, which is just going to take this initial account, which I gave a lot of tokens, going to query the operator address. And so this is the crucial thing here, right? This is delegating on the provider from a provider account to the provider delegator. So without Interchain Security, this is just going to change power on the provider. With Interchain Security, we see this power change transmitted also to the consumer, which is then forwarded to Tendermint on the consumer, right? So let's see if we can get this working. Fingers crossed. Okay, so let's see. Yeah, so this looks like transaction sent, okay. And I think we might get it. What I should have done is shown before and after, but yeah, we can already see it. So I've delegated 800,000 tokens here. Voting power is kind of derived from that with some scalar. It's like a 1 million token factor. So now we have the voting power change, as expected on the provider and reflected also in the consumer. So just we can see that working again, just do the same thing again. So now we can see voting power 8,000 on the consumer. If we're lucky, we might catch it before. Okay, no, it's fast enough, it's already changed. So we've already seen the increase in power there. So that's it. For this demo, I'm not going to show things like slashing. If you slash, you could slash the consumer. This slash will be transmitted to the provider, be reflected in a change in validator power on the provider. And then that change as well would also funnel down again to the consumer. So, but yeah, simple demo. We have V1 releasing hopefully within days. And we're on a fast release cycle, so we should be able to see V2, V3 in the weeks to follow. So that's it for the live demo. I hope you guys can try that out. You can edit your own consumer chain to try that. I'll just show you quickly what the code looks like for that. So this is my workspace. Maybe if you're developing, you'd like a similar setup. So I have each of the dependencies cloned, so I can change and debug those more easily. Like for example, you can use in Golang, you can replace dependencies with a local copy, so you can more easily debug, right? So that's what's going on there. Looking at Interchain Security itself, we have two apps that are kind of the default apps. For the purposes of this demo, we're on the HackATOM branch. I've got this consumer app with a kind of like hello module. So if you've ever used Ignite CLI and followed the tutorial there, this shows you how to, it starts very simple, hello world. It goes through a blog post application, which is exactly what's here. So if you want to just immediately start writing custom consumer chains, like today, this is the place to start. You can just edit this hello module, clone this module, write arbitrary logic in here. So that's that. Okay, so I think that's it. I'm just going to check I haven't forgotten anything. Yeah, so here are some links. HackATOM to get started right away today. Ignite, I do recommend Ignite if you want to kind of get started with SDK development, because it does a lot of things for you. It can generate boilerplate for you. It's well written, etc. We have a consumer chain tool, which is in the works, which is this tool which takes care of running a new smart contract chain. We will also be releasing the incentivized testnet soon, so this is going to allow validators to receive like real rewards for carrying out certain actions in the testnet to get this thing tested really, really thoroughly. I think that I was going to do a code dive, but actually I think better to leave it here. Thank you. So just to finish, Interchain Security, high performance app logic, safely, securely, and easily. It's almost here, and it's going to be awesome. Thank you.
PC project now. I will explain my background briefly. I'm a full-stack developer with over 12 years of diverse experience in software, including embedded software, web application, big data, and IoT. I have been a blockchain technology believer since 2017, with initial blockchain development on Ethereum DApp and Hyperledger Fabric. I gained solid low-level blockchain knowledge and multiple cross-chain project experience after joining Octopus Network in 2020, especially the application on Cosmos and Substrate blockchain. Today, we are going to explore the first solution to directly enable transfers of fungible token and encapsulated data between a Substrate blockchain and a Cosmos-based blockchain. Our solution supports a direct relationship between the Substrate and Cosmos chains with independent layers. Here's the agenda of the workshop. There are two parts in the workshop. Part 1 is Substrate IBC architecture introduction, which is the column PPT in front of you. Part 2 is code demo of Substrate IBC fungible token transfer. Here's the brief background on Substrate and Cosmos and their light comparison. For those unfamiliar, Substrate is a framework for modelizing runtimes in a blockchain. This concept was designed by Gavin Wood, founder of Parity Technologies, an organization cultivating the Proctor ecosystem. Separately, the Cosmos SDK is a framework for utilizing IBC, Tendermint, and other economic controls like governance, slashing, staking, etc. Developed by Interchain Foundation and its partner. The Cosmos hubs are flexibly accepting this in different arrangements for Cosmos relationship. Both modular blockchain concepts are viable for similar use cases, especially when considering solutions for application-specific blockchains. There are some differences in between as well. One key feature of Substrate is Off-chain worker. Substrate software has an advantage in executing off-chain activity in trusted manner through off-chain worker. Off-chain workers have special low latency relationship to a Substrate validator. And through this extended trusted and flexibility, we have enabled an IBC library and relayer. Here's the off-chain worker activity diagram. The off-chain worker already integrated in substrate IPC project. Here's the fundamental logic of Option Worker. From here, the outside world uses JSON RPC to interact with substrate node. All modification to state will be handled using transaction from substrate node or from Option Worker to the runtime logic. Runtime logic has full read-write capability to runtime storage and write capability to Option Worker. Please note the runtime logic doesn't have the capability to read Option storage because the data in Option storage is not agreed by the blockchain network through consensus. Substrate node can read and write directly to Option storage. Even though the node can read Option data, there is no impact to the runtime logic, as the way by which a node writes to runtime logic through transaction, which needs to be agreed upon consensus. Option workers can read and write Option storage directly. But can only read runtime storage directly. Option worker can submit transaction to update the state on the chain, which is runtime storage. Option worker can call external service to get corresponding data back and update the chain state or Option storage. In substrate IPC, some incoming packets were stored in Option storage and will be queried by the relayer. Here's the substrate IPC scope. The red box in the diagram represents the scope of the substrate IPC project. The scope includes two parts, the substrate part and the relayer part. The substrate part includes development of substrate IPC palette, BC Light Client in IBC-RS, fungible token transfer in IBC-RS, and the integration of substrate IBC palette with IBC-RS. The relayer part includes support for substrate and development of Octopus XT, which communicates with substrate IBC palette. The standards in IBC core, including ICS02 client, ICS03 connection, ICS04 channel and packet, ICS05 port, and ICS26 router were all implemented in the first two milestones, upon which the most important IPC standard, ICS20, is built. More IPC standards, like Interchain account, will be implemented in the substrate IPC palette in the future. The substrate IPC palette, a modular component of substrate, provides IPC-related capabilities, including creating clients, connections, channels, etc. Substrate application developers can import this palette to utilize the capabilities above with minimal configuration or adaptations. The relayer and IBC-RS was initially designed for Cosmos only, so there are some incompatibilities with substrate. For example, they use proto-buffer for serialization. In substrate, the serialization mechanism is scale codec, This results in some different label and format of the same event. For example, IBC event is from IBCIS and event is from substrate node itself. Both refer to the same thing. Here's the events from IBC channel handshakes. If you are new to IBC, reviewing the documents will show that it's not too different from standing up a VPN. The channelization and encapsulation of data is begun with an OOB agreement. Conceptually, this handshake sequence is very similar to the tunneling provided by a virtual private networks. This is necessary to sync with either far-end chain to verify the correct value and to bring up a channel between two network endpoints. Most of you are likely familiar with messages for managing the first steps in opening a channel. In substrate log, channel open init, try acknowledgement and confirm messages can all be found with some details for debugging in the event log. Here, the revision client version describes a nonce for the revision number. This improves accountability and awareness for both parties to assure that the upgrades to the client on either side will increment here. Separately, revision high is a block number incrementing. Here's the IBC fungible token transfer flow. Here we can see the flow logic between two substrate channels using IBC, dual relayer and IBCRS when transferring fungible token after the channel is brought up. This design requires a relayer to stabilize the connection in most cases. Start from here. A user submits a transaction to chain A. After the transaction request is routed to IBCRS and get processed later, the write reaccess of on-chain data will be handled by IBC palette. Then IBC palette will emit and send packet event. The relayer detects the send packet event, then submits a receive packet transaction to chain B. The chain B handles the receive packet transaction request with similar routes previously and emits an event write acknowledgement. The relayer detects the write acknowledgement event and submits an acknowledgement transaction to chain A. The diagram displays two IBCI's invocation flow, sending fungible token and receiving fungible token. The flow logic applies to most IBC transactions. Here's another example of IBC invocation flow, update client. Step 1, an update client transaction was submitted to deliver function in IBC palette. The deliver function is the most important dispatchable function in IBC palette. Step 2, the transaction is passed to IBC-RS routing module. When processing the transaction, IBC-RS calls a client reader interface to query the client state in step 3, which is implemented in IBC Palette. This flow applies to most of the IBC standard transactions. That's all for the substrate IBC architecture introduction. Please continue to watch the subsequent video for IBC token transfer demo. Thank you.